Okay, today we're going to do our last related rates problem for a while. We have a particle moving along a hyperbola x times y equals 8. As it reaches the point 4, 2, so x equals 4 and y equals 2, the y coordinate is decreasing at a rate of 3 centimeters per second. How fast is the x coordinate of the point changing at that instant? So I've gone ahead and already drawn a Cartesian plane, but we're going to do a diagram because if you remember, it's diagram, rates, equations, derivative, and simplify. So diagram is our first step. So I'm going to kind of tie that to rates because we're also going to be writing down sort of what else we know. So the first thing that we know is we have a hyperbola. Now, this hyperbola is going to go like this and like this. So this kind of isn't that important right here, but it is there. So you should realize that. And then, it's just a sketch, but we kind of got one of these things going, right? It doesn't look very good, but you get it. It's supposed to be straight. You know what? Let me redo that. It seems kind of important that that would be correct. That doesn't look right. Well, tools are quite something. Okay, and now there we go. That's more like it. So we have this hyperbola. Now, ideally, these would look more similar, but we know that the equation for this hyperbola is x times y equals 8. What else do we know? We know that at the point 4, 2, which is that is the instance that we are at the point 1, 2, 3, 4, 4, 2, you get a good color for that. That'll be right here. And then it'll be, well, ideally it would be above 1. So let's fix it. Well, it's just a sketch. It'll be like right here, right? Now let's not make it look like that's 1. 1 is like somewhere there. So we have this point right here. We have a hyperbola. We have a particle that is moving down this hyperbola right here, okay? And we know that the rate at which it is decreasing on the y-axis is 3 centimeters per second, which means we have the change in y over the change in time. What does that mean? We know that dy by dt is 3 centimeters per second. Well, that's important. We're going to need that. What else do we know? We know x and we know y because x is 4 and y is 2. Y is 2. This is a really ugly yellow. I don't like my choice of color. So we have this equation and it could look nicer. I mean, we could use it like this. We could just use implicit differentiation on this, but I don't like it. So we have x times y equals 8. This isn't even a better yellow. Let me just go to orange. I'm done with this shenanigans. So we're going to rewrite this. We're going to just divide by y. Actually, is that smart? Yes, we're going to divide by y. I wanted to divide by x, but let's do both. If we divide by y, we get x equals 8 over y. And if we divide by x, then we get y equals 8 over x. Now, which one do we want to use? Let's get to that in a minute, and let's just go back a couple steps and write down what we want to find. What do we want to find? We know the change in y over the change in time. What we want to find is how fast the x coordinate of the point is changing at this point 4, 2, which means we want to find the change in x over the change in time. The rate of change of x. That's what we want to find. So what do we do now to find that? Well, we have an equation here. And it turns out we really do want to use this equation right here because we're going to want to use implicit differentiation to get the rate of x, and it's already alone on one side. We don't even have to isolate it. So that's makes life much easier, right? So we're just going to use implicit differentiation, and we're going to end up with the change in x over the change in time equals equals the derivative with respect to t of 1 over y times 8. And if you recall, you can just take that 8 out, so it'll become 8 times the derivative of 1 over y. And that is going to become y. Let's make that y to the negative 1 because that's a lot easier. So that's going to become 8 times the derivative with respect to t of y to the negative 1. Now we're going to use the power rule, but we're also going to have to use, I believe, the chain rule. Yes, because there's a variable mismatch. If this were just y and we could plug it in, fine. But no, there's a negative 1 up here. So we're going to have to differentiate it. But with respect to t, there's going to be some complication there. So the first thing that we're going to do now is we're going to just start to simplify. And let me write down the correct notation here because we're looking for this at a certain point. We're looking for the change in x over the change in time at a certain point, at the point when x equals 4 and y equals 2. So we can just plug those in. And yes, we're going to use the chain rule while we do it. And we're going to write that down first, actually, I think. So that's 8 times the change in y over the change in time times, well, I probably shouldn't write that first. That'll be confusing for people who don't have a great grasp of the chain rule. So the outer function is t to the negative 1, which means we're taking that down, right? So we're going to make that negative 1 times the inner function, which is y. And we're going to multiply that and then to the negative 2. And we're going to multiply that by the derivative of the inner function, which is the rate of change of y, which we have over here. So we can just plug that in later. Okay, well, let's not get confused about what's happening where here. I mean, it's all multiplication, sure, but there's a lot of arguments. So what's going to happen here? What's going to happen here is that we're going to multiply this negative through. Actually, if we don't multiply it through, we can get rid of it. So let's keep it. Let's make this 8 times negative 1 over y squared. Negative 1 over y squared. Well, when we plug in y, that negative is going to go away. Times 3 centimeters per second, because that's our rate of change of y, right? So now what do we want to do with this here? Now we want to really plug in x. So if we plug in x and y, actually we really don't need to plug in x. We're looking for the change of rate of x, so it doesn't matter. We're just going to plug in y. So we're going to end up with 8 times 1 over negative 2 squared times 3 centimeters per second. Well, that negative is going to go away, and we're going to end up with 8 times 1/4 times 3 centimeters per second. I'm going to go ahead and just simplify that. I don't need to do every single step. We're going to end up with 8 times 3 over 4 centimeters per second, which is going to simplify to 6 centimeters per second. So that's our final solution. The change in x over the change in time, or the rate of change of x, is 6 centimeters per second at this instant when the particle is at the point 4, 2. So I hope that was helpful, and I'll link some more related rates videos in the end of this video.